Hello everyone again and welcome to my channel, and in here we're going to talk about heterolysis to electrophiles and nucleophiles. Now you might be wondering, what are all those three terms right there talking about heterolysis? First, let's look at a specific atom which is mainly familiar with everyone, the one and only carbon. And you see carbon usually has 4 electrons, and to have a stable octet it must bond in some way or another with an atom that donates 1 electron each to form sharing and resulting in bonding. So in this case what we have is a neutral carbon atom. Now what happens is that carbon can exist in a particular molecule as just a neutral state with 0 charge, and it can actually form another type of carbon where it has a positive charge with just 3 bonds, and it can also form a negative charge by gaining a lone pair with 3 bonds right there. This is actually highly linked to the formal charge of carbon and how they exist. So in this particular part we actually going to see how this can actually be transformed using heterolysis to generate different forms of carbon charges. So first here is carbon forms 2 different ions when a heteroatom is bonded to carbon, and that bond actually cleaves. So it's important to note that, and through this illustration where first of all we have usually a carbon here bonded to some 3 substituents, and then there is 1 substituent here that is a heteroatom. We'll just notify as Y. What we notice here is that Y is a good leaving group sometimes, and what happens is that it has a dipole moment that is negative, partial negative charge, and the carbon by convention has a partial positive charge. So as a result of this, what happens is that this bond actually cleaves and forms a lone pair on the Y, and this process of the bond cleaving is called heterolysis, because we have an heteroatom that's actually being cleaved from the carbon atom right there, which in this case is shown here. So as a result, what we generate is carbon actually losing electrons, and that becomes the generation of a positive charge on the carbon. And so if you look at the geometry here, you notice that it is a trigonal planar compound in here, and what we form as well is a good leaving group which has a negative charge on it with a lone pair, which is Y. So in this particular case, this particular carbon with a positive charge is called a carbocation, and since it is termed to be carbocation, it's known to be electron deficient. Now since you notice this is actually happening, let's look at another case scenario where we have our carbon and is bonded to, let's say, another type of a Y species, which is a heteroatom. So in here we're going to use a different color to actually illustrate that. We have a carbon here, and in this case what is happening instead is that we have a different heteroatom attached to the carbon. Now in this part, when you have the dipole moment actually switched around in such a way that carbon has or is more electronegative in this case than our Y species right here as a heteroatom, what happens as a result is that we cleave this bond and it forms a lone pair on the carbon. So as a result, through heterolysis, or some people might say heterolysis, you actually form a product which is of this nature, where we have our carbon with a lone pair and the negative charge, and we have the form of carbon ion right there, and our other product is our Y that actually has a positive charge on it. So in this case, what we are categorizing this particular carbon with an anion on is called a carboanion, and this is considered to be an electron-rich species. Now, since you're able to notice these two categories in here, category 1, which is the formation of a carbocation, which is this right there, and category 2, which is the formation of a carbanion, which is an electron-rich species, we're going to see the characteristics of a carbocation versus that of carbanion. First characteristic is that they are actually short-lived for a specific carbocation, so they have a short lifespan, which means that they are mostly intermediate in any chemical reaction, and as a result of this, it's known to be highly reactive. In this particular case, once you notice that, you actually need to be able to understand that this reactivity is highly linked to carbocations reacting with mainly Lewis bases, and also they are considered to be electrophiles. Now, what do I mean by electrophiles? What I mean by electrophiles is that they are actually species that are actually electron loving. So since they are electron loving, like phile, which means loving, and electron, which means negative charged, it means that they need to be able to fill the valence shell, or the valence shell, yes, and to fill the valence shell they have to gain electrons from somewhere. So in this case, once you notice these characteristics of a carbocation, which is that they are mainly or mostly electrophiles, let's look at the other part, which is a carbanion. So in this case, for carbanions, they are actually proton seekers, so that means they take protons. And second step is to note that they actually also seek a positive center. So this will be important in our examples that we're going to show later in this particular video. So in here they seek positive charge. Also, they actually donate electrons, mainly the electron pair. So the combination of these two here actually is a big characteristic of the other name, which is called nucleophile. So in this part, nucleophile means that they actually, this species carbanions, they love a nucleus, and you know what the charge of a nucleus is. Charge is positive, so they will actually seek positive charge in this particular part, and they will be able to actually perform or act as a Lewis base, while on this other side here they actually act as Lewis acids, carbocation. Let's look at the first case scenario, which is an example in here. So we have an example where we have a carbon here, and this carbocation has a positive charge and is going to be reacting with a base that has a negative charge. So what you notice here is that in this particular part we actually have this to be the Lewis acid, and also it has a carbocation. So in conclusion, this will actually act as an electrophile, and on the other side we actually have the electrophile reacting with a Lewis base which has a carbanion. We don't know whether the base contains carbon, but we notice a negative charge, and by default this is known to be the nucleophile. So in this case, the nucleophile is nucleus loving, which means it seeks the proton or positive charge, and it goes in and interacts with this to actually form a specific compound which is of this particular nature, with RB bonded to our carbon center right there. So in this particular case, an example of these will be, for example, we have dimethylamine, and this is going to be reacting with boron fluoride or boron trifluoride. And what you notice here is that boron here will have a partial positive charge, and these fluorides will have partial negative charges around. So this particular amine here has a nitrogen with lone pairs, and by default this is considered to be the Lewis base, which has a carbon anion that is not visible, but due to how electronegative it is, the nitrogen, this actually makes it to be a strong nucleophile. So in this case, what happens is that our lone pair, which are electrons, will be attracted to the boron center, because the boron center has the positive charge on it, and what that results in is the formation of a nitrogen with a bond attached to the boron, and we have our fluoride all attached right there. You can ignore the lone pairs around the fluorides, and then we have a methyl group with a hydrogen right there. Therefore, this makes the nitrogen here to have a positive charge and our boron to have a negative charge. So the second example here is actually a type where we have, instead of this particular carbocation, we actually have a carbonyl group, and in this case the carbonyl group will be subjected to a compound with a negative charge, in this case B, with lone pairs and negative charge. So what do you notice here? In this case, by default we know this already to be the Lewis base, and this in this case has an anion, therefore making this in conclusion to be the nucleophile. And what happens is that the nucleophile with the electrons is attracted to the positive side of this particular carbonyl group, which is a ketone, where the carbon has a partial positive charge and the oxygen has a partial negative charge. So these will actually interact with this carbon, and then this double bond, one of the bond will actually form a lone pair on the oxygen, and this particular species is considered, based on the analysis, that it is a Lewis acid. It has a partial positive charge, so we'll consider this to be a carbocation, and in conclusion this becomes the electrophile. So as a result, what we get is our product which has oxygen with a negative charge and the lone pairs, and then we actually have a bond with the carbon. This carbon is bonded to the base, and this is bonded to the methyl group. So an example of this is actually shown here, where we have a specific phenyl group, and this phenyl group is bonded to a specific branch that is actually aldehyde. So in this case, this aldehyde here will be subjected to a specific cyanide here, where we have the nitrogen with the lone pair, and this carbon has a negative charge on it. Since through our analysis we notice this carbon here to have a partial positive charge, making this oxygen to have a partial negative charge, this automatically is our Lewis acid that actually have a partial positive charge, so a carbocation. As a result, it is an electrophile, while this our other cyanide has a carbon negative charge with the lone pair. Therefore, the lone pair makes it to actually act as a nucleophile that comes in and attracts itself to this particular partial positive charge on the carbonyl. So in this case, this acts as a Lewis base that has a carbocation and acting as a nucleophile, and as a result this actually bond forms a lone pair, one of it, and results in the formation of our product, which is shown right here. So that's about it for this particular long video. Hope you're able to actually have a grasp and understanding on how nucleophiles are actually created and electrophiles based on carboanions and carbocations in various reactions, mainly during heterolysis. So all the same, stay smart, believe yourselves, and hit the comment section and let me hear your thoughts and any suggested sample questions that you might have. All the same, see you on my next video.